What caused the Big Bang? Tonight, we're going to explore the most profound question in all of science. You've probably heard about the Big Bang countless times, how our universe exploded into existence 13.8 billion years ago. But here's what most people don't realize. We have absolutely no idea what actually caused it to happen. The moment before the beginning remains a complete mystery that challenges our deepest understanding of reality itself. By the end of this journey, you're going to understand exactly why this question might be impossible to answer, and why that makes it even more fascinating. Before we dive in, if you enjoy these kinds of cosmic explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Let's begin. Picture Albert Einstein in 1915, working through the mathematical foundations of what would become general relativity. He wasn't thinking about the birth of the universe. He was trying to understand gravity itself, and what he discovered changed everything. Einstein realized that what we experience as gravity isn't actually a force pulling objects together. Instead, mass and energy curve the very fabric of space and time. Think about this for a moment. The space around you right now, the air between your fingers, the distance from your eyes to these words, all of it is part of a flexible, bendable fabric that massive objects warp and twist. Einstein's equations describe this curvature with unprecedented precision. They predicted how light would bend around the sun, how time would slow in strong gravitational fields, how the cosmos itself must behave. But there was something in those equations that even Einstein didn't initially want to accept. When he first worked through the mathematics, the equations told him something remarkable and disturbing. The universe couldn't be static. Space-time itself, according to his own theory, had to be either expanding or contracting. There was no mathematical solution that allowed for a perfectly still, unchanging cosmos. Einstein found this idea so troubling that he did something almost unprecedented in his career. He modified his own equations. He added what he called the cosmological constant, a kind of mathematical fidget factor that would allow the universe to remain perfectly balanced and eternal. At the time, this seemed reasonable. After all, the universe appeared stable and unchanging. Stars shone steadily in their constellations. Nothing suggested that space itself might be growing larger every second, but the universe had other plans. In Russia, a mathematician named Alexander Friedmann was working through Einstein's original equations without the cosmological constant. In 1922, just 7 years after Einstein published General Relativity, Friedmann discovered something extraordinary hidden in the mathematics. The equations had solutions that described expanding universes, cosmos that grew larger with time, space itself, stretching and carrying matter along for the ride. Friedmann's solutions weren't just mathematical curiosities. They described 3 possible fates for our universe. It could expand forever. It could expand and then contract back to a single point. Or it could hover at the precise balance between the two. But in all cases, the universe was dynamic, not static. 5 years later, in 1927, a Belgian physicist and Catholic priest named Georges Lemaitre independently reached similar conclusions. But Lemaitre went further. He proposed that if the universe was expanding now, then in the past, it must have been smaller. And if you extrapolated backward far enough, there must have been a moment when everything we can observe was compressed into what he called the primeval atom, a state of unimaginable density and temperature from which space and time themselves began to expand. The idea was radical, almost absurd. The entire observable universe, all the galaxies and stars and planets, emerging from something smaller than an atom. But Lemaitre's mathematics were sound, and his vision would prove to be remarkably prescient. The real breakthrough came in 1929, when an American astronomer named Edwin Hubble made an observation that changed our understanding of the cosmos forever. Hubble was studying the light from distant galaxies, measuring something called redshift, the way light from objects moving away from us gets stretched to longer, redder wavelengths. It's the same Doppler effect that makes an ambulance siren sound deeper as it drives away from you, but applied to light instead of sound. What Hubble discovered was astonishing. Nearly every galaxy he observed showed redshift, meaning they were all moving away from us. But more than that, the farther away a galaxy was, the faster it was receding. This wasn't random motion. It was a systematic pattern that pervaded the entire observable universe. Imagine you're standing in the middle of a vast field and everyone around you starts walking away. The person closest to you moves slowly. Someone twice as far away moves twice as fast. Someone 3 times as far away moves 3 times as fast. That's exactly what Hubble saw happening with galaxies across the cosmos. The mathematical relationship Hubble discovered is now called Hubble's law, and it quantifies exactly how fast the universe is expanding. For every 26 million light-years of distance, galaxies recede about 43 miles per second faster. This number, known as Hubble's constant, tells us the current rate at which space itself is stretching. But here's the crucial insight that took scientists time to fully grasp. This expansion doesn't mean galaxies are flying through space away from us. Instead, space itself is expanding, carrying the galaxies along like raisins in rising bread dough. New space is constantly being created between galaxies, making the distances between them larger, while the galaxies themselves remain relatively unchanged. This expansion has no center, at least not in the 3-dimensional space we can observe. If you could transport yourself to any galaxy in the universe, you would see all the other galaxies moving away from you in exactly the same pattern Hubble observed from Earth. It's not that we're at the center of the universe, it's that every point in space experiences the same expansion. When Einstein learned of Hubble's discovery, he reportedly traveled to California to see the evidence for himself. What he found forced him to confront the fact that his original equations had been correct all along. The universe was indeed dynamic, expanding just as the mathematics had predicted. He later called the cosmological constant his greatest mistake, recognizing that he had let philosophical preferences override the pure logic of his own theory. Hubble's observations meant something profound. If the universe is expanding now, it must have been smaller in the past. And if you could somehow run time backward, there must have been a moment when all the matter and energy we observe was compressed into an infinitely small, infinitely dense point. The universe had a beginning. Interestingly, the term Big Bang wasn't coined by supporters of the theory. In 1949, astronomer Fred Hoyle, who favored an alternative called the steady-state model, used Big Bang as a dismissive label during a BBC radio broadcast. Hoyle's steady-state theory proposed that new matter was continuously created to maintain constant density as the universe expanded, avoiding the need for a definite beginning. He thought the idea of a cosmic birth moment was preposterous. But the evidence kept mounting. In 1948, physicists Ralph Alpher and Robert Herman made a remarkable prediction. If the universe really had emerged from a hot, dense state, they calculated, it should have left behind a kind of afterglow, radiation from the primordial fire that gave birth to everything. This radiation would have been incredibly hot initially, but after billions of years of cosmic expansion, it should have cooled to about 9 degrees above absolute zero, permeating all of space like a fossil echo of creation itself. For nearly 2 decades, this prediction remained untested. The technology didn't exist to detect such faint cold radiation spread uniformly across the sky. But in 1965, 2 radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, accidentally stumbled upon exactly what Alpher and Herman had predicted. Penzias and Wilson were trying to eliminate background noise from a sensitive radio antenna, but they kept detecting a persistent signal that seemed to come from everywhere at once. The signal had a temperature of about 4.9 degrees above absolute zero, remarkably close to the theoretical prediction. After ruling out every possible source of interference, including pigeon droppings on their antenna, they realized they had discovered the cosmic microwave background radiation, the afterglow of the Big Bang itself. This discovery was revolutionary. Here was direct observational evidence that the universe had once been in a hot, dense state. The radiation showed the perfect spectrum of what physicists call a blackbody, exactly what you'd expect from matter and energy in thermal equilibrium at high temperature, then cooled by billions of years of expansion. More observations followed, each one adding detail to our understanding. Satellites like COBE, WMAP, and Planck mapped this ancient light with ever-increasing precision, revealing tiny fluctuations in temperature, variations of just a few millionths of a degree that represent the seeds from which all cosmic structure would eventually grow. The cosmic microwave background radiation is remarkably uniform across the entire sky, confirming that the early universe was incredibly smooth and homogeneous. But those tiny temperature variations, imprinted when the universe was only 380,000 years old, mark regions that were slightly denser or less dense than average. Over billions of years, gravity would amplify these small differences, turning them into the galaxies, stars, and planets we see today. What emerged from decades of observations was a coherent picture. The Big Bang wasn't an explosion in space, it was the beginning of space itself. Time, distance, matter, and energy all emerged together from an initial state of unimaginable density and temperature. The expansion we observe today is the continuation of that primordial stretching of space-time that began 13.8 billion years ago. This transformation from mathematical theory to observational science represents one of humanity's greatest intellectual achievements. What started as abstract equations describing the curvature of spacetime became a detailed understanding of how everything we observe came to exist. The Big Bang model successfully explains the expansion of the universe, the cosmic microwave background radiation, and the abundances of the lightest elements. Three independent lines of evidence that all point to the same conclusion. But even as this picture became clear, it raised deeper questions. If we could trace the expansion back to its beginning, what would we find? What existed before space and time began? What could cause the universe itself to come into being? These questions push us to the very limits of physics, into a realm where our most fundamental theories begin to break down. And that's where our journey into the deepest mystery of existence truly begins. But before we can grapple with what might have caused the Big Bang, we need to understand just how convincing the evidence for expansion really is. The galaxies themselves tell this story. They function as cosmic markers scattered across space and time, each one carrying testimony about the fundamental nature of the universe we inhabit. When Hubble first observed galactic redshift, he was seeing something profound. Galaxies aren't just moving away from us randomly. They're participating in a systematic expansion where distance and recession speed are perfectly correlated. A galaxy located about 326 million light-years away recedes at roughly 4,350 miles per second. Double that distance, and the recession speed doubles too. Triple the distance, triple the speed. This isn't coincidence. It's the signature of space itself, growing larger. Think about what this means for a moment. If you could somehow freeze time and measure the distance to a distant galaxy, then wait a billion years and measure again, that galaxy would be farther away, even though it hasn't moved through space. New space has been created between you and that galaxy, stretching the distance like an invisible tide that never stops flowing. There's something beautifully counterintuitive about our nearest major galactic neighbor, Andromeda. Located about 2.5 million light-years away, it's actually moving toward us, not away. You might think this breaks the expansion pattern, but it doesn't. At relatively small scales, and 2.5 million light-years counts as small in cosmic terms, local gravitational attraction can overpower the expansion of space. Andromeda and the Milky Way are bound together in a slow-motion gravitational dance that will eventually bring them together in about 4.5 billion years. But step back to larger scales, and the expansion dominates everything. When astronomers look at distant galaxies, they're essentially operating a time machine. Light travels at 186,182 miles per second, incredibly fast, but not instantaneous. The light reaching your eyes right now from a galaxy 10 billion light-years away began its journey when the universe was less than a quarter of its current age. You're seeing that galaxy as it existed billions of years ago, when the cosmos was younger, denser, and very different from today. The most distant galaxy ever observed, called GNZ11, appears as it was when the universe was only about 400 million years old. The light we're seeing from this galaxy has been traveling toward us for over 13 billion years, crossing an almost incomprehensible expanse of space that has continued expanding throughout its entire journey. When that light began its trip, the universe was a much smaller, more crowded place. This is where the concept of redshift becomes truly remarkable. As light travels through expanding space, the expansion stretches the light waves themselves. Imagine a wave drawn on a rubber sheet. As you stretch the sheet, the wavelength gets longer. The same thing happens to light crossing cosmic distances. Blue light gets stretched toward red light gets stretched toward infrared, and infrared gets stretched even further into radio waves. Astronomers measure this stretching using a value called redshift Z. A galaxy with redshift Z-1 means its light has been stretched by a factor of 2. The universe has literally doubled in size during the time that light was traveling toward us. Galaxies with higher redshifts show us even more ancient epochs, when the universe was smaller and matter was more densely packed together. The Hubble Space Telescope revolutionized our ability to measure cosmic distances by identifying specific types of variable stars called Cepheids. These remarkable stars pulse with a brightness that's directly related to their intrinsic luminosity. By comparing how bright a Cepheid appears to how bright it actually is, astronomers can calculate its distance with remarkable precision. Cepheids became the cosmic standard candles that allowed us to calibrate the entire distance scale of the universe. Even more powerful are Type Ia supernovae, stellar explosions so bright they can be seen across billions of light-years. These occur when a white dwarf star in a binary system accumulates enough material from its companion to trigger a runaway nuclear explosion. Because the physics of this process is so consistent, Type Ia supernovae all reach nearly the same peak brightness, making them excellent standard candles for measuring vast cosmic distances. In 1998, two teams of astronomers studying distant supernovae made a discovery that stunned the scientific community. They found that the most distant supernovae appeared fainter than expected based on their redshifts. This could only mean one thing: the expansion of the universe wasn't just continuing, it was actually accelerating. The universe is growing larger at an ever-increasing rate. This acceleration implies the existence of something called dark energy, a mysterious form of energy that makes up about 68% of the universe. Unlike matter, which gravitationally attracts and should slow expansion down, dark energy has a repulsive effect that pushes space apart faster and faster. We can observe its effects clearly but we have almost no idea what it actually is. Modern surveys have plotted the distances and recession velocities of hundreds of thousands of galaxies, creating detailed Hubble diagrams that confirm the linear relationship between distance and speed. These observations span enormous ranges of cosmic distance and time, and they all tell the same story. Space has been expanding for billions of years, and that expansion is now accelerating. Even entire clusters of galaxies, containing thousands of individual galaxies bound together by gravity, participate in this cosmic expansion. While the galaxies within a cluster remain gravitationally bound to each other, the clusters themselves move apart as space expands between them. It's like cities staying intact, while the highways connecting them grow longer. Some galactic structures are truly staggering in scale. The Sloan Great Wall, a filamentary structure of galaxies stretching about 1.4 billion light-years across, demonstrates that even the largest gravitationally bound structures are carried along by the expansion. Space grows in the gaps between these massive structures while preserving their internal architecture. Quasars, the incredibly luminous cores of distant galaxies powered by supermassive black holes, provide windows into the most ancient observable epochs. Some quasars show redshifts greater than 7, meaning we're seeing them as they existed when the universe was less than 800 million years old. Their light has been traveling toward us for over 13 billion years, stretched and reddened by the relentless expansion of space. The expansion has left other subtle signatures scattered throughout the cosmos. Gravitational lensing, where massive galaxy clusters bend and magnify the light from even more distant objects behind them, allows us to peer further back in time than would otherwise be possible. These natural cosmic telescopes reveal galaxies so distant and ancient that they formed when the universe was still in its infancy. There are even fossilized sound waves preserved in the current distribution of galaxies. In the dense, hot plasma of the early universe, sound waves created regular patterns of compression and rarefaction. When the universe cooled enough for atoms to form, these acoustic patterns became frozen into the matter distribution, leaving a subtle but measurable imprint on how galaxies are clustered today. These baryon acoustic oscillations provide an independent cosmic ruler that confirms our measurements of expansion. Individual galaxies also carry more subtle motion beyond the Hubble flow. Their peculiar velocities, movements additional to the cosmic expansion, reveal the gravitational influence of massive but invisible structures made of dark matter. Our own local group of galaxies is being pulled toward a massive concentration of matter about 150 million light-years away, nicknamed the Great Attractor. Multiple independent techniques for measuring cosmic distances all converge on the same picture. Whether astronomers use the surface brightness of elliptical galaxies, the behavior of planetary nebulae, or the properties of globular star clusters, they consistently find the same pattern of expansion and the same cosmic distance scale. By comparing apparent brightness with redshift for objects at different cosmic epochs, astronomers can trace not just the current expansion rate, but its entire history. These observations reveal that the expansion was actually decelerating for the first several billion years after the Big Bang, as gravity from all the matter in the universe gradually slowed it down. Only in the more recent past has dark energy's repulsive effect begun to dominate, causing the acceleration we observe today. Observations of galaxies at different cosmic epochs also reveal how the universe has evolved chemically and structurally over time. Early galaxies were smaller, more irregular, and contained fewer heavy elements than modern galaxies. The peak era of star formation occurred when the universe was about 3 billion years old, and stellar activity has been gradually declining ever since as the available gas gets consumed or dispersed. What emerges from this vast web of observations is a remarkably consistent and detailed picture. We live in an expanding universe that began from a hot, dense state about 13.8 billion years ago. The expansion has been stretched space itself, carrying galaxies along like islands of matter in a growing ocean of space-time. Multiple independent lines of evidence, galaxy redshifts, cosmic microwave background radiation, light element abundances, large-scale structure, and many others, all point to the same fundamental conclusion. This convergence of evidence from completely different observational techniques has transformed cosmic expansion from a theoretical hypothesis into one of the best established facts in all of science. The galaxies themselves serve as witnesses, their light carrying testimony across billions of years and billions of light years, to tell us the story of how space and time have been growing since the beginning. This network of observational evidence transforms the expansion of the cosmos from theoretical speculation into firmly established observational fact, supporting the entire framework of modern cosmology. But there's another piece of evidence that's even more remarkable than galactic redshifts, a faint whisper of light that fills every corner of space, carrying within it the direct fingerprint of the universe's birth. This is the cosmic microwave background radiation, the oldest light we can ever hope to detect, and it represents our most direct window into the primordial cosmos. To understand what this ancient light tells us, we need to travel back in time to when the universe was just 380,000 years old. That might sound like a long time, but in cosmic terms, it's an instant, less than 3/1000% of the universe's current age. At that epoch, everything we can observe today was compressed into a volume millions of times smaller than it is now. The universe at that time was unimaginably different from today. Instead of the cold, mostly empty space we're familiar with, punctuated by islands of matter we call galaxies and stars, the entire cosmos was filled with a dense, hot plasma. Imagine the interior of the sun, but extending everywhere, a sea of protons, electrons, and photons, all interacting violently in thermal equilibrium at a temperature of about 5,400 degrees Fahrenheit. In this primordial plasma, light could not travel freely. Photons would stream through space for only tiny fractions of an inch before colliding with a free electron and scattering in a random direction. The universe was completely opaque, like trying to see through the heart of a star. No light could propagate in straight lines across any significant distance, so there could be no images, no shadows, no visual structure of any kind. But as the universe expanded and cooled, something remarkable happened. When the temperature dropped to about 5,400 degrees Fahrenheit, conditions became just right for protons and electrons to combine into neutral hydrogen atoms for the first time. This process, called recombination, was like a cosmic phase transition that changed everything. Suddenly, with almost all the free electrons locked up inside atoms, photons could travel freely through space. In what must have been one of the most dramatic moments in cosmic history, the universe went from completely opaque to perfectly transparent in a relatively brief period. The sea of trapped light was instantly liberated, streaming outward in all directions through the newly transparent cosmos. That flash of light from recombination is still traveling through space today. But after 13.8 billion years of cosmic expansion, those photons have been stretched from visible light into microwave radiation. What began as the brilliant glow of a universe-sized furnace has been redshifted and cooled to just 4.9 degrees above absolute zero, minus 454 degrees Fahrenheit. This cosmic microwave background radiation fills all of space uniformly. Right now, as you read these words, about 400 million of these ancient photons pass through every square inch of your body each second. They've been traveling since before the Earth existed, before the sun formed, before any of the stars we see in our night sky began to shine. You are constantly bathed in the afterglow of creation itself. The discovery of this radiation was entirely accidental. In 1965, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were trying to eliminate sources of noise from a sensitive horn antenna they wanted to use for satellite communications. But they kept detecting a persistent signal that seemed to come from everywhere at once, a faint hiss that corresponded to a temperature of about 6.3 degrees above absolute zero. At first, they assumed it was some kind of interference. They checked their electronics. They cleaned bird droppings off the antenna. They even considered whether pigeons nesting in the horn might somehow be responsible for the signal. But no matter what they did, the mysterious radiation remained, constant and unchanging, coming equally from all directions in the sky. What Penzias and Wilson had stumbled upon was exactly what theoretical physicists Ralph Alpher and Robert Herman had predicted in 1948. If the universe had really emerged from a hot, dense state, there should be leftover radiation from that primordial fireball, cooled by billions of years of expansion to just a few degrees above absolute zero. When the connection was finally made, it was revolutionary. Here was direct observational evidence not just that the universe was expanding, but that it had actually been in a hot, dense state in the distant past. The radiation showed the precise spectrum expected from matter in thermal equilibrium, what physicists call a perfect blackbody spectrum. This couldn't have been produced by any astrophysical process that occurred after the Big Bang. It was truly primordial. The cosmic microwave background is remarkably uniform across the entire sky. Over 99.99% of the radiation has exactly the same temperature in every direction, confirming that the early universe was incredibly smooth and homogeneous. But hidden within this near-perfect uniformity are tiny fluctuations, temperature variations of just a few 10,000ths of a degree, that carry profound information about the birth and early evolution of the cosmos. These minute temperature variations represent density fluctuations in the primordial plasma. Regions that were slightly denser than average appear very slightly warmer in the cosmic microwave background, while regions that were less dense appear very slightly cooler. The difference is tiny, about 0.01 or 18 degrees Fahrenheit. But those small variations contain the seeds of all the cosmic structure we see today. In 1992, NASA's Cosmic Background Explorer satellite, known as COBE, first mapped these fluctuations across the entire sky. The Discovery team's leader, George Smoot, famously called the patterns they found the handwriting of God, because these tiny ripples in the cosmic microwave background represent the earliest structures we can ever hope to observe, the gravitational seeds from which galaxies, stars, and ultimately planets and life would eventually grow. More sophisticated missions followed, each revealing greater detail in the ancient light. The Wilkinson Microwave Anisotropy Probe, or WMAP, operated from 2001 to 2010, mapping the cosmic microwave background with unprecedented precision. The European Space Agency's Planck mission, launched in 2009, pushed sensitivity even further, detecting temperature variations as small as a few millionths of a degree. These observations revealed something extraordinary about the geometry of space itself. The way acoustic waves propagated through the primordial plasma left characteristic patterns in the cosmic microwave background, patterns that tell us the universe is geometrically flat. Space doesn't curve back on itself like the surface of a sphere, nor does it curve outward like a saddle. On the largest scales, the geometry of our universe is as flat as a sheet of paper. The cosmic microwave background also preserves fossil sound waves from the early universe. In the dense plasma before recombination, sound waves could propagate, creating alternating regions of compression and rarefaction. The speed of sound in that primordial medium was about 1/3 the speed of light, which meant acoustic waves could travel at most about 150,000 light-years before recombination froze them in place. This acoustic horizon, the maximum distance sound could travel before recombination, shows up today as a characteristic angular scale in the cosmic microwave background. Features separated by about 1 degree on the sky correspond to regions that were exactly one sound horizon apart when the universe became transparent. This provides cosmologists with a standard ruler that allows precise measurements of cosmic distances and the expansion history. The polarization of the cosmic microwave background carries even more information. Just as sunglasses can filter polarized light, sensitive detectors can measure the polarization patterns imprinted on the ancient radiation. These patterns tell us about conditions in the primordial plasma, how it was moving, whether magnetic fields were present, and potentially even whether gravitational waves from the very earliest moments of the Big Bang left detectable signatures. Scientists have detected one type of polarization pattern called E-modes, which confirms our understanding of density fluctuations in the early universe, but they're still searching for B-mode polarization patterns, which would provide direct evidence for gravitational waves generated during cosmic inflation, the hypothetical period of exponential expansion that may have occurred in the first fraction of a second after the Big Bang. Experiments around the world are pushing the sensitivity of cosmic microwave background observations to ever greater extremes. At research stations in Antarctica, where the dry, cold air minimizes atmospheric interference, arrays of superconducting detectors scan the sky looking for the faint polarization patterns that would confirm our theories about the universe's first moments. The cosmic microwave background also reveals our motion through space. Because we're moving with respect to the rest frame defined by this ancient radiation, we observe a subtle temperature difference between the direction we're moving toward and the direction we're moving away from. This dipole anisotropy tells us that our entire local group of galaxies is moving at about 230 miles per second toward a distant concentration of matter in the direction of the constellation Hydra. Even galaxy clusters leave their mark on the ancient light. When cosmic microwave background photons pass through the hot gas surrounding galaxy clusters, they get slightly energized in a process called the Sunyaev-Zeldovich effect. This creates tiny distortions in the background radiation that allow astronomers to map the distribution of hot gas in the universe and measure cosmic distances through an entirely independent method. The absence of certain types of distortions in the cosmic microwave background spectrum is almost as important as what we do detect. The radiation shows no significant departures from a perfect thermal spectrum, which tells us that very little energy was injected into the universe between the time of recombination and the formation of the first stars. This validates our understanding of the Dark Ages, the period between cosmic transparency and the birth of the first luminous objects. Gravitational lensing by dark matter structures subtly distorts the patterns we see in the cosmic microwave background. Just as a magnifying glass bends and focuses light, massive concentrations of invisible dark matter bend the paths of cosmic microwave background photons, creating slight distortions that provide a direct map of dark matter distribution throughout the universe. The cosmic microwave background has become our most important tool for precision cosmology. Its detailed study has determined fundamental parameters of our universe, its age, composition, geometry, and expansion rate with remarkable accuracy. We now know the universe is 13.98 billion years old, contains about 5% ordinary matter, 27% dark matter, and 68% dark energy, and has a geometry so close to perfectly flat that any curvature is undetectable. This unique window into the primordial universe continues to provide precise data for testing cosmological models, constraining fundamental physics, and discovering new phenomena at the frontier of human knowledge. But the cosmic microwave background radiation tells us only part of the story of the universe's earliest moments. To truly understand what happened in the beginning, we need to go even further back in time, to an era so ancient and extreme that the very elements that make up our world were being forged in the primordial fire of creation itself. During the first 20 minutes after the Big Bang, the entire universe was a nuclear reactor. Temperatures and densities were so extreme that atomic nuclei could be created directly from the collision of individual protons and neutrons. This epoch, called Big Bang nucleosynthesis, was the only time in cosmic history when conditions throughout the entire universe were suitable for nuclear fusion on a cosmic scale. To understand what happened during those crucial first minutes, we need to journey back to when the universe was just 1 second old. At that moment, the temperature throughout all of space was about 18 billion degrees Fahrenheit, roughly 1,000 times hotter than the core of the Sun. At these incredible temperatures, protons and neutrons existed in thermal equilibrium, constantly converting back and forth through weak nuclear interactions. The balance between protons and neutrons at this time was determined by their slightly different masses and the ambient temperature. Neutrons are about 0.114% more massive than protons, and this tiny difference meant that in the primordial plasma, there were about 7 protons for every neutron. This ratio would prove crucial for determining the composition of all the matter we see today. As the universe continued to expand and cool, something critical happened. The rate of expansion became faster than the rate of weak interactions that could convert protons to neutrons, and vice versa. When this occurred, the ratio of neutrons to protons became frozen in at about 1 neutron for every 7 protons. But neutrons, when they're not bound inside atomic nuclei, are unstable. Free neutrons decay with a half-life of about 10.3 minutes, spontaneously converting into protons, electrons, and neutrinos. As the universe continued to expand and cool during those first few minutes, the neutron population was steadily declining while waiting for conditions to become just right for nuclear fusion to begin. The key moment arrived when the universe was about 100 seconds old. By this time, the temperature had dropped to about 8 billion degrees Fahrenheit, still incredibly hot, but cool enough for the first composite atomic nucleus to form and survive. This first nucleus was deuterium, heavy hydrogen, consisting of 1 proton bound to 1 neutron. Deuterium formation was the critical bottleneck for all subsequent nuclear reactions. Before this moment, any deuterium nuclei that might have formed were immediately destroyed by the intense radiation filling the universe. High-energy photons would blast apart these fragile 2-particle nuclei as quickly as they could form. But once the temperature dropped sufficiently, deuterium could finally accumulate. With a supply of deuterium available, nuclear reactions could proceed rapidly. Deuterium nuclei collided with other protons and neutrons, triggering a cascade of fusion reactions. Deuterium plus deuterium could produce tritium, heavy hydrogen with 2 neutrons, plus a proton. Deuterium plus tritium could fuse to create helium-4, releasing a neutron in the process. These reactions occurred with remarkable efficiency once they got started. The result was that approximately 25% of all the protons and neutrons in the universe were fused into helium-4 nuclei during this brief period. This is a robust prediction that depends very little on the details of cosmological models. It's determined primarily by the neutron-to-proton ratio and basic nuclear physics. Today, when we observe the composition of matter throughout the universe, we find that about 25% of ordinary matter is indeed helium-4, in excellent agreement with this prediction. This primordial helium abundance is one of the strongest pieces of evidence for the Big Bang theory. Stars can produce helium through nuclear fusion in their cores, but stellar nucleosynthesis alone could never account for the large amount of helium we observe everywhere in the universe. The only way to explain why a quarter of all ordinary matter is helium is if it was produced in the hot, dense conditions of the early universe. Small amounts of other light elements were also produced during Big Bang nucleosynthesis. Lithium-7 was created through reactions like tritium plus helium-4, but only in tiny quantities, roughly 1 lithium nucleus for every 10 billion hydrogen nuclei. Trace amounts of helium-3 and deuterium also survived this primordial nuclear furnace. There was a fundamental limit to how heavy the elements produced during Big Bang nucleosynthesis could be. No stable atomic nuclei exist with mass numbers 5 or 8, creating an insurmountable gap that prevented fusion reactions from building elements heavier than lithium. By the time the universe was 20 minutes old, it had expanded and cooled so much that nuclear fusion reactions ceased entirely, permanently freezing the abundances of the light elements at their primordial values. The universe emerged from this nuclear epoch with a composition that was remarkably simple. About 75% hydrogen, 25% helium-4, 0.01% deuterium, and traces of helium-3 and lithium-7. Everything else, all the carbon, oxygen, iron, and other heavy elements that make planets and life possible, would have to wait billions of years to be forged in the nuclear furnaces of stars. Modern observations allow us to measure these primordial abundances with remarkable precision. Astronomers study regions of the universe that have been least affected by stellar processing, places like blue compact dwarf galaxies and pristine gas clouds that have remained largely unchanged since the early universe. By extrapolating measurements from these metal-poor regions back to zero metallicity, they can determine what the primordial element abundances must have been. Deuterium is particularly valuable for these studies because it's easily destroyed in stars but never created in significant amounts by stellar nucleosynthesis. The deuterium we observe today in pristine gas clouds is essentially a fossil remnant from Big Bang nucleosynthesis. Measurements of deuterium absorption lines in the spectra of distant quasars reveal that about 2.5 parts per million of all hydrogen nuclei are actually deuterium. This deuterium abundance tells us something profound about the density of ordinary matter in the universe. The amount of deuterium produced during Big Bang nucleosynthesis depends sensitively on how many protons and neutrons were available for nuclear reactions. More matter means more collisions and more efficient fusion, which destroys deuterium. Less matter means less efficient fusion, and more deuterium survives. The observed deuterium abundance indicates that ordinary matter, the protons and neutrons that make up atoms, comprises about 4.9% of the critical density needed to make the universe geometrically flat. This determination is completely independent of observations of the cosmic microwave background radiation, yet it gives almost exactly the same answer. The agreement between these two very different methods provides powerful confirmation of our understanding of cosmic evolution. Helium-4 abundances measured in metal-poor regions also match theoretical predictions remarkably well. Observations indicate that about 24.7% of ordinary matter by mass is helium-4, very close to the 25% predicted by Big Bang nucleosynthesis calculations. There is one puzzling discrepancy, however. Theoretical calculations predict that lithium-7 should be about 2.5 times more abundant than what we actually observe in the most metal-poor stars. This lithium problem might indicate that our understanding of stellar physics is incomplete. Perhaps these ancient stars have depleted their surface lithium through mixing with their interiors. Alternatively, it might hint at new physics beyond the standard model that operated during the era of primordial nucleosynthesis. Laboratory experiments with particle accelerators help refine our theoretical understanding by measuring the rates of nuclear reactions that were important during Big Bang nucleosynthesis. These experiments allow physicists to test and improve their calculations of primordial element production, ensuring that theoretical predictions are as accurate as possible. The sensitivity of light element abundances to cosmological parameters makes Big Bang nucleosynthesis an extraordinarily powerful test of our models. If the number of neutrino species had been different, or if fundamental constants had different values during the first few minutes, the predicted element abundances would disagree with observations. The excellent match between theory and observation validates our understanding of both nuclear physics and cosmology during this crucial epoch. Modern computational models of Big Bang nucleosynthesis include networks of hundreds of nuclear reactions tracking the detailed evolution of element abundances as the universe expands and cools. These sophisticated calculations can predict not just the final abundances of light elements, but their entire production history during those first 20 minutes. The success of Big Bang nucleosynthesis places tight constraints on alternative cosmological models. Any theory that attempts to explain the universe's origin must also explain why we observe exactly the abundances of light elements that Big Bang nucleosynthesis predicts. This requirement has ruled out many alternative scenarios and strongly supports the standard model of cosmology. Future observations with ever greater precision will continue to test these predictions. As measurements of primordial abundances become more accurate, they may reveal subtle signatures of physics beyond the standard model or provide new insights into the conditions that prevailed during the universe's first moments. This primordial nuclear era directly connects modern astronomical observations with extreme physical processes that occurred when the universe was younger than a 20-minute-old child. The success of Big Bang nucleosynthesis demonstrates how laboratory physics can be extrapolated to understand cosmic processes at scales of energy and time completely inaccessible to direct human experience. But even those first 20 minutes of nuclear fusion represent a relatively late chapter in the universe's story. To truly understand how the cosmos came to exist, we need to venture into an even more extreme and mysterious epoch, a period so brief and violent that it challenges our deepest understanding of space, time, and reality itself. Between about 100 billionth of a trillionth of a trillionth of a trillionth of a second and 1 billionth of a trillionth of a trillionth of a second after the Big Bang, something extraordinary may have happened. The universe might have undergone a period of exponential expansion so rapid and dramatic that it defies ordinary comprehension. This hypothetical epoch is called cosmic inflation, and if it really occurred, it would fundamentally change how we think about the birth of everything we observe. During this incomprehensibly brief moment, regions of space smaller than a subatomic particle could have expanded to dimensions larger than a basketball. In fact, the expansion factor during inflation might have been at least 10, followed by 26 zeros, a number so large that if you wrote it out in normal-sized digits, the string of numbers would stretch for millions of miles. The driving force behind this exponential expansion would have been a hypothetical energy field called the inflaton field. Unlike ordinary matter or radiation, this field would have possessed a nearly constant energy density that didn't dilute as space expanded. This property, energy density that remains constant while space grows, creates a kind of anti-gravity effect that can drive exponential expansion of space-time itself. This expansion wouldn't have violated Einstein's relativity because nothing was actually moving faster than light. Instead, space itself was stretching at an accelerating rate, carrying any matter or energy along for the ride. It's similar to how two ants on an inflating balloon can separate faster than either ant is actually walking, because the balloon's surface is expanding between them. Inflation was first proposed in 1981 by physicist Alan Guth to solve several puzzling problems with the standard Big Bang model. One of these problems is called the horizon problem. When we look at the cosmic microwave background radiation, we find that regions of the sky that are separated by vast distances all have almost exactly the same temperature. But according to the standard Big Bang model, these regions should never have been in thermal contact with each other. Here's why this is puzzling. Light can only travel a finite distance in a finite time. In the 380,000 years between the Big Bang and the emission of the cosmic microwave background, light could have traveled at most 380,000 light years. But we observe regions in the cosmic microwave background that are separated by distances much larger than this light travel distance, yet they still have the same temperature to within a few 10,000ths of a degree. How did such distant regions manage to reach thermal equilibrium if they were never in causal contact? Inflation provides an elegant solution. If the universe underwent exponential expansion very early in its history, then regions that appear causally disconnected today were actually in close thermal contact before inflation began. The exponential expansion then stretched them apart faster than light could travel between them, preserving their thermal equilibrium while making them appear causally disconnected. Inflation also solves what's called the flatness problem. Observations tell us that the geometry of our universe is remarkably close to being perfectly flat, neither curved like a sphere nor curved like a saddle, but flat like a sheet of paper. In standard Big Bang cosmology, achieving this near-perfect flatness would require incredibly precise fine-tuning of initial conditions. But inflation naturally produces flat universes. Any initial curvature of space would be stretched and diluted by the exponential expansion, just as the curved surface of a balloon appears flat if you inflate it to an enormous size and examine only a small patch. After sufficient inflation, any universe would appear geometrically flat to its inhabitants. Perhaps most remarkably, inflation can explain the origin of all cosmic structure through quantum mechanics. The inflaton field, like all quantum fields, would have experienced tiny quantum fluctuations, random variations in energy density at the smallest possible scales. Normally, these fluctuations would be far too small to have any observable consequences. But during inflation, these microscopic quantum fluctuations would have been stretched to macroscopic scales. Fluctuations that started smaller than 4x 10^34 inches, far smaller than an atomic nucleus, could have grown to scales of light years or more. These amplified quantum fluctuations would have created the tiny density variations that we observe in the cosmic microwave background radiation, and that eventually grew into galaxies, stars, and planets. This connection between quantum mechanics and cosmology is profound. The largest structures in the universe, the cosmic web of galaxies stretching across billions of light years, might have originated as quantum fluctuations in a field that existed for less than a billionth of a trillionth of a trillionth of a second. The predictions of inflation can be tested through detailed observations of the cosmic microwave background. Different models of inflation make specific predictions about the spectrum of fluctuations they produce. The spectrum is characterized by an index that describes how the amplitude of fluctuations varies with their size. Simple inflation models predict an index very close to, but not exactly equal to, 1. Observations from the Planck satellite have measured this spectral index with remarkable precision, finding a value of about 0.968. This is consistent with the predictions of inflation, but it also rules out the simplest possible inflation models, which predict an index closer to 1.0. The data favor more sophisticated models where the inflaton field has a carefully shaped potential energy function. Another key test of inflation involves searching for primordial gravitational waves. During inflation, quantum fluctuations in the gravitational field itself would have been amplified, creating gravitational waves that should still be propagating through the universe today. These primordial gravitational waves would leave a distinctive signature in the polarization patterns of the cosmic microwave background radiation. The search for this B-mode polarization signature represents one of the most important frontiers in observational cosmology. Its detection would provide direct evidence that inflation actually occurred and would reveal the energy scale at which it happened. Several experiments, including ground-based arrays in Antarctica and planned space missions, are pushing toward the sensitivity needed to detect or rule out these primordial gravitational waves. There are many different models of how inflation might have worked. Chaotic inflation, developed by André Linde, shows how inflation could begin from random initial conditions without requiring special fine-tuning. Hybrid inflation involves multiple interacting fields that can produce more complex dynamics. String theory attempts to embed inflation within the framework of fundamental physics by using higher dimensional objects called branes. Some models suggest that inflation might be eternal. In these scenarios, inflation never completely ends everywhere at once. Instead, it continues in some regions while stopping in others, creating a vast multiverse of bubble universes, each with potentially different physical laws and constants. Our observable universe would be just one bubble in this infinite cosmic foam. The end of inflation would have been as dramatic as its beginning. When the inflaton field finally rolled down to the bottom of its potential energy curve, all that stored vacuum energy would have been converted into ordinary particles and radiation through a process called reheating. This would have populated the universe with the hot, dense plasma that we observe in the cosmic microwave background radiation, and that underwent Big Bang nucleosynthesis. Not everyone accepts inflation as the correct explanation for cosmic origins. Alternative theories such as cyclic cosmology propose that our universe emerged from the collision of higher dimensional objects, or that it underwent a period of slow contraction followed by a bounce into expansion. These models attempt to solve the same problems as inflation, but through different mechanisms. Computer simulations of inflation incorporate the complex physics of quantum field theory to calculate detailed predictions for observations. These simulations can predict not just the spectrum of density fluctuations, but also subtle features like non-Gaussianity, departures from the purely random distribution that simple inflation models would produce. Current observations place tight limits on how much non-Gaussianity exists in the cosmic microwave background. The fluctuations appear to be very nearly perfectly Gaussian, which rules out many exotic inflation models and supports simpler scenarios where a single field drives the exponential expansion. Future observations will continue to test inflation with ever-increasing precision. Space missions like LightBird and ground-based experiments like CMB S4 will search for B-mode polarization with unprecedented sensitivity. Large-scale structure surveys will map the distribution of galaxies with exquisite detail, providing additional tests of inflation's predictions. If confirmed through the detection of primordial gravitational waves, inflation would represent one of the most remarkable successes of theoretical physics. It would validate the idea that quantum mechanics and general relativity, when combined properly, can explain the origin and evolution of the entire observable universe. Inflation also raises profound philosophical questions about the nature of reality. If eternal inflation is correct, then our universe is just one bubble in an infinite multiverse, where every possible outcome occurs somewhere. This would fundamentally change how we think about our place in the cosmic order and the meaning of physical laws. The concept of inflation represents one of the most audacious ideas in modern physics, the proposal that the entire observable universe emerged from a microscopic quantum fluctuation that was exponentially amplified in the first instant of time. This connection between quantum mechanics at the smallest scales and cosmic structure at the largest scales exemplifies the deep unity of physics across all scales of energy and size. The success of inflation in resolving multiple conceptual problems of the standard Big Bang model has established its central position in modern cosmology, even as questions remain about its specific implementation. If confirmed by future detections of primordial gravitational waves, inflation would represent an extraordinary triumph of theoretical physics in predicting and explaining fundamental properties of the observable cosmos. But even if inflation solved the puzzle of how the universe began, it left behind a cosmos that was still dark and featureless. After the brief, violent birth of space and time, after the primordial nuclear furnace had forged the first light elements, the universe entered what astronomers call the cosmic dark ages, a period that stretched from about 380,000 years to roughly 400 million years after the Big Bang, when the cosmos was transparent but contained no sources of light. During this long, quiet epoch, the only illumination came from the fading glow of the cosmic microwave background radiation. This ancient light, already stretched from visible wavelengths to infrared by cosmic expansion, grew redder and dimmer with each passing million years. The universe was cooling rapidly as it expanded, dropping from the 5,400 degrees Fahrenheit of recombination to just a few dozen degrees above absolute zero. At these frigid temperatures, nothing dramatic could happen. It was too cold for hydrogen atoms to be ionized by thermal motion, but still too warm for the first molecules to form in any significant quantities. The cosmos had become a vast, dark ocean of neutral hydrogen and helium gas, stirred only by the invisible gravitational pull of dark matter. Yet even in this seemingly empty darkness, the seeds of future complexity were taking root. The tiny density fluctuations imprinted during inflation were growing stronger under their own gravitational attraction. Dark matter, which interacts only through gravity, began to collapse into the first cosmic structures, invisible scaffolding upon which all future galaxies and stars would eventually be built. Computer simulations reveal that the first dark matter halos capable of forming stars needed to reach masses of at least 1 million times that of our Sun. These halos grew through a process astronomers call hierarchical structure formation. Smaller clumps of dark matter merged together to form progressively larger structures, like tributaries flowing into rivers and rivers flowing into vast cosmic watersheds. As these dark matter halos collapsed under their own gravity, they began to capture and concentrate the surrounding hydrogen and helium gas. But for this gas to eventually form stars, it needed a way to cool down and condense. In the modern universe, heavy elements like carbon and oxygen provide efficient cooling, but the primordial gas contained almost no heavy elements at all. Instead, cooling had to rely on much less efficient processes. Hydrogen atoms could radiate away small amounts of energy through electronic transitions, but the most important coolant was molecular hydrogen, H2. These simple molecules, consisting of 2 hydrogen atoms bound together, could radiate energy much more effectively than individual atoms. The formation of molecular hydrogen in the primordial universe required a delicate chemistry involving trace amounts of free electrons and negatively charged hydrogen ions. These reactions proceeded slowly in the rarefied gas of the Dark Ages, but they were crucial for creating the first molecules in cosmic history and enabling the gas to cool enough for star formation to begin. When gas clouds within dark matter halos reached critical densities of about 16,000 particles per cubic inch. Something remarkable finally happened. The gas began to fragment under its own gravity, breaking up into smaller and smaller clumps as it continued to cool and condense. At the centers of these fragments, the first protostars began to form. The stars that emerged from this process were unlike anything we see in the universe today. Called Population 3 stars, they were primordial giants with masses typically 100 to 1,000 times greater than our Sun, composed entirely of hydrogen and helium with no heavy elements whatsoever. They were the first nuclear furnaces to ignite in the cosmic darkness. These massive stars burned with incredible intensity. In their cores, temperatures reached 180 million degrees Fahrenheit, nearly 10 times hotter than the center of the Sun. But without heavy elements to help them radiate away excess heat, they couldn't maintain the delicate balance between gravity and radiation pressure that allows smaller stars to burn steadily for billions of years. Population 3 stars lived fast and died young. Their enormous masses meant they burned through their nuclear fuel in just a few million years before ending their lives in catastrophic explosions. Some became supernovae of unimaginable violence, while others may have collapsed directly into the first black holes without any explosion at all. But their brief lives had profound consequences for the future evolution of the universe. For the first time since Big Bang nucleosynthesis, nuclear fusion was creating elements heavier than lithium. In the extreme conditions at the cores of these massive stars, carbon, oxygen, silicon, iron, and other heavy elements were being forged through successive rounds of nuclear burning. When these stars died, they scattered their heavy element riches throughout space. Supernova explosions hurled newly minted atoms across thousands of light years, contaminating the pristine primordial gas with what astronomers call metals, any element heavier than hydrogen and helium. This chemical enrichment fundamentally changed the physics of gas cooling and star formation for all subsequent generations. The ultraviolet radiation from these first massive stars also began to transform the universe on larger scales. Their intense light was energetic enough to strip electrons away from hydrogen atoms, reionizing the neutral gas that had formed during recombination. This began a cosmic phase transition called the Epoch of Reionization, which gradually transformed the universe from neutral back to ionized over several 100 million years. Ancient quasars also contributed to this reionization process. These incredibly luminous objects, powered by supermassive black holes with masses billions of times that of the Sun, appeared surprisingly early in cosmic history. How such massive black holes formed so quickly remains one of astronomy's great mysteries. They may have grown from the direct collapse of enormous gas clouds, or from the remnants of the first population 3 stars. The first galaxies were very different from the majestic spiral and elliptical galaxies we observe today. They were small, irregular, and compact systems that formed stars at rates 10 to 100 times faster than similar mass galaxies in the modern universe. These galactic building blocks were violent places, with stellar winds and supernova explosions constantly stirring up their gas and occasionally expelling it entirely into intergalactic space. Galaxy mergers were common in the early universe. When these primitive star-forming systems collided and merged, they triggered intense bursts of star formation that could consume most of their gas in just a few million years. These cosmic construction projects rapidly built up stellar mass while feeding material into the central black holes that would eventually power quasars. The James Webb Space Telescope has revolutionized our view of this ancient epoch. Its infrared eyes can peer through cosmic dust and detect galaxies with redshifts greater than 10, showing us the universe as it existed when it was less than 500 million years old. These observations reveal that massive galaxies formed surprisingly early, challenging theoretical models that predicted a more gradual buildup of cosmic structure. Spectroscopic observations of these early galaxies reveal extreme physical conditions. Emission lines from hydrogen and oxygen trace radiation fields far more intense than anything seen in nearby galaxies, while the heavy element abundances are thousands of times lower than in modern systems. These ancient galaxies were laboratories for physics under conditions that no longer exist anywhere in the observable universe. Even today, we can study relics of this primordial epoch in our own cosmic neighborhood. The oldest globular clusters in the Milky Way preserve stellar populations that formed during the first billion years after the Big Bang. These dense balls of ancient stars serve as archaeological sites where we can study the properties of primordial star formation. The Milky Way's stellar halo also contains extremely metal-poor stars that are likely survivors from the earliest generations of star formation. By analyzing the chemical composition of these stellar fossils, astronomers can reconstruct the history of heavy element production and galaxy formation in our local regions of the universe. This transition from darkness to light represents one of the most fundamental phase changes in cosmic evolution. Over the course of several 100 million years, the universe transformed from a simple sea of primordial gas into a complex ecosystem containing the first stars, galaxies, black holes, and heavy elements. The gravitational seeds planted during cosmic inflation had finally grown into luminous structures that could synthesize the chemical ingredients necessary for planets and life. The feedback cycles established during this epoch, where star formation creates heavy elements and energy that regulate future star formation, would continue to operate for billions of years. The patterns of structure formation set in motion during the cosmic dawn created the foundation for the large-scale architecture of the modern universe, from individual galaxies to vast clusters and the cosmic web itself. This era established the fundamental patterns of structure formation that would continue for billions of years, creating the galaxies, clusters, and large-scale structure of the modern universe. But there was something puzzling about the way these cosmic structures behaved. As astronomers began to study galaxies more carefully, they discovered that the visible stars and gas weren't providing nearly enough gravitational pull to hold these systems together. The universe seemed to be hiding most of its matter in some invisible form that could only be detected through its gravitational effects. This mysterious component, which we now call dark matter, makes up about 27% of the universe, more than 5 times as much as all the ordinary matter we can see. Despite its gravitational dominance, dark matter remains completely invisible to telescopes. It doesn't emit light, it doesn't absorb light, and it doesn't reflect light at any wavelength. We know it exists only because of how it shapes the cosmic structures around it. The first hints of dark matter came from studying how stars orbit within spiral galaxies. In the 1970s, astronomer Vera Rubin and her colleague Kent Ford made detailed measurements of stellar velocities in galaxies like Andromeda. According to Newton's laws, stars farther from the galactic center should orbit more slowly, just as the outer planets in our solar system move more slowly than the inner ones. But that's not what Rubin and Ford observed. Instead, they found that stars maintained roughly the same orbital speed regardless of their distance from the galactic center. Stars at the edge of visible galaxies were moving so fast that they should have been flung out into intergalactic space long ago, unless there was much more mass present than could be accounted for by visible stars and gas. The implications were staggering. These observations suggested that every galaxy was embedded in a massive halo of invisible matter extending far beyond the visible stellar disk. For the Milky Way, this dark matter halo has a total mass of about 1 trillion times that of our Sun, stretching out to distances of about 650,000 light-years, more than 3 times the diameter of the visible galaxy. Even more compelling evidence comes from gravitational lensing. Massive objects bend space-time, causing light from background sources to follow curved paths. When astronomers observe distant galaxies through clusters of galaxies in the foreground, they can map exactly how much mass is present in the cluster by measuring how the background light is distorted. The results consistently show far more mass than can be accounted for by visible matter. In some cases, like the famous bullet cluster, astronomers can actually see the dark matter and ordinary matter separated from each other. When 2 galaxy clusters collided at speeds of millions of miles per hour, the hot gas in each cluster was slowed down by electromagnetic interactions, while the dark matter passed right through unaffected, creating a clear spatial separation between the 2 components. Computer simulations of cosmic structure formation confirm that dark matter must exist. Models that include only ordinary matter cannot reproduce the large-scale structure we observe in the universe, but simulations that include cold dark matter, particles that move slowly compared to the speed of light and interact only through gravity, successfully recreate the cosmic web of galaxies and galaxy clusters that we see today. These simulations reveal that dark matter forms a vast scaffolding throughout the universe. It creates gigantic filaments connecting dense nodes where galaxy clusters form, separated by nearly empty voids. This cosmic web spans billions of light-years and provides the framework within which ordinary matter can accumulate to form stars and galaxies. Dark matter halos follow remarkably universal properties. Regardless of their total mass, they all have similar density profiles, dense central regions that gradually thin out toward the edges, following a predictable mathematical pattern. These halos also contain numerous smaller sub-halos, remnants of past mergers that continue to orbit within the larger structure. Many of these sub-halos may contain small satellite galaxies. The Milky Way has dozens of known satellite galaxies, like the Large and Small Magellanic Clouds, but simulations predict there should be hundreds of dark matter subhalos in our local region. This discrepancy, known as the missing satellite problem, suggests either that most small dark matter halos fail to form visible stars, or that our understanding of dark matter physics is incomplete. The motions of these satellite galaxies provide additional evidence for dark matter. By measuring how fast they orbit around the Milky Way, astronomers can determine the mass and extent of our galaxy's dark matter halo. These measurements confirm that the halo extends to distances of at least 650,000 light-years and contains far more mass than all the stars in our galaxy combined. Dark matter also leaves subtle imprints in the distribution of ordinary galaxies. The same acoustic oscillations that we see in the cosmic microwave background radiation are preserved as statistical patterns in how galaxies cluster together today. These baryon acoustic oscillations provide a standard ruler that allows precise measurements of cosmic distances and confirms our understanding of how dark matter structures evolved over billions of years. What exactly is dark matter made of? The leading candidates are hypothetical particles called WIMPs, weakly interacting massive particles, that were predicted by extensions of the standard model of particle physics. These particles would have masses between about 1 and 1,000 times that of a proton and would interact with ordinary matter only through gravity and the weak nuclear force. Deep underground laboratories around the world are searching for direct evidence of WIMP interactions. Experiments like LIEX Zeppelin use tanks of ultra-pure liquid xenon surrounded by massive shielding to detect the incredibly rare occasions when a WIMP might collide with an atomic nucleus. So far, these searches have not detected any confirmed WIMP interactions, placing increasingly strict limits on their possible properties. Other experiments look for indirect signs of dark matter annihilation. When two dark matter particles collide and destroy each other, they might produce high-energy gamma rays, neutrinos, or antimatter particles that could be detected by space-based telescopes or underground neutrino detectors. Several promising signals have been reported over the years, but none have been definitively confirmed as dark matter. Alternative candidates include axions, extremely light particles that could form a kind of cosmic background field. Unlike WIMPs, axions would behave more like waves than individual particles, potentially forming large-scale condensates that could explain dark matter's gravitational effects without requiring direct particle interactions. Some scientists have proposed that dark matter might not exist at all. Modified theories of gravity, such as MOND, modified Newtonian dynamics, suggest that the laws of gravitation might behave differently at very low accelerations, producing effects that mimic the presence of invisible matter. However, these alternative theories struggle to explain all the observational evidence, particularly the behavior of colliding galaxy clusters like the Bullet Cluster. The cosmic web of dark matter creates tidal streams that we can observe in our own galaxy. When small satellite galaxies are torn apart by the Milky Way's gravity, their stars form long streams that trace the gravitational field of the dark matter halo. These stellar streams provide detailed maps of how dark matter is distributed throughout our local cosmic neighborhood. Future surveys will map billions of galaxies to trace dark matter's influence with unprecedented precision. Projects like the Dark Energy Survey and the European Space Agency's Euclid mission will measure how the shapes of distant galaxies are subtly distorted by gravitational lensing from foreground dark matter structures. These weak lensing measurements will create three-dimensional maps of dark matter distribution throughout a significant fraction of the observable universe. The detection of dark matter particles would revolutionize our understanding of fundamental physics. It would provide the first confirmed example of matter beyond the standard model and would bridge the gap between particle physics and cosmology in ways we can barely imagine. The discovery might reveal entirely new forces and interactions that operate on cosmic scales. Yet even if we never detect dark matter particles directly, their gravitational effects have already taught us profound lessons about the universe. Dark matter governs the formation and evolution of every visible structure in the cosmos, from individual galaxies to the largest galaxy clusters. Without dark matter's gravitational scaffolding, the universe would be a very different and much emptier place. Understanding the true nature of dark matter remains one of the greatest challenges in both cosmology and particle physics. Its resolution promises deep insights into the fundamental laws of nature and may reveal connections between the microscopic world of elementary particles and the macroscopic architecture of the cosmos. Dark matter connects the physics of elementary particles with the large-scale architecture of the universe, exemplifying the profound unity between seemingly disparate scales of physical reality. But as profound as dark matter's influence is on cosmic structure, it represents only about 27% of the universe's total content. There's an even more mysterious component that dominates everything else, something that makes up roughly 68% of all energy and matter in the cosmos, yet remained completely unknown until just a few decades ago. This enigmatic component is called dark energy, and its discovery fundamentally changed our understanding of the universe's past, present, and ultimate fate. Unlike dark matter, which acts as gravitational glue holding cosmic structures together, dark energy appears to have the opposite effect. It's driving the acceleration of cosmic expansion, pushing space itself apart at an ever-increasing rate. the discovery came as a complete shock in 1998. Two independent teams of astronomers were studying Type Ia supernovae A, stellar explosions that occur when white dwarf stars accumulate enough matter from companion stars to trigger runaway nuclear fusion. These cosmic detonations are remarkably consistent in their peak brightness, making them excellent standard candles for measuring cosmic distances. The teams, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, were expecting to find that the expansion of the universe was gradually slowing down. After all, gravity from all the matter in the universe should be acting like a cosmic brake, gradually decelerating the expansion that began with the Big Bang. They were planning to measure how much this deceleration had changed the expansion rate over cosmic time. But when they compared the distances to remote supernovae with their redshifts, they found something completely unexpected. The distant supernova appeared systematically fainter than they should have been if the universe's expansion were decelerating. This could only mean one thing: the expansion of the universe wasn't slowing down, it was speeding up. The implications were staggering. Something was overpowering the gravitational attraction of all the matter in the universe and driving cosmic expansion to accelerate. This discovery was so revolutionary that it earned the 2011 Nobel Prize in Physics and forced cosmologists to confront the existence of an entirely new component of reality. The simplest explanation for this acceleration is something called the cosmological constant, the same mathematical term that Einstein had introduced into his equations in 1917 to allow for a static universe. In this interpretation, empty space itself possesses a kind of intrinsic energy density that creates a repulsive gravitational effect. This vacuum energy has negative pressure, and according to general relativity, negative pressure creates anti-gravity. The amount of dark energy required to explain the observed acceleration is extraordinarily small by everyday standards. Its density is only about 4x 10 to the base 30 pounds per cubic foot, roughly equivalent to one proton in a volume the size of a telephone booth. Yet this tiny energy density spread throughout all of space is enough to accelerate the expansion of the entire observable universe against the gravitational pull of all its matter. This creates one of the most severe problems in theoretical physics. When physicists calculate how much vacuum energy should exist based on quantum field theory, they get answers that are about 10 to the 120 times larger than what we observe. This is the largest discrepancy between theory and observation in the history of science, a mismatch so extreme that it suggests our understanding of either quantum mechanics or gravity must be fundamentally incomplete. Alternative models propose that dark energy might not be a constant property of space. These quintessence theories suggest that dark energy could be a dynamic field that changes over time, similar to the inflaton field that may have driven cosmic inflation in the early universe. Such fields could have pressures that are negative, but less extreme than the cosmological constant, and they might evolve as the universe ages. Even more exotic possibilities include phantom energy, where the pressure is more negative than the energy density itself. If such phantom energy exists and grows stronger over time, it could lead to a catastrophic future scenario called the Big Rip. In this nightmare outcome, dark energy would eventually overcome not just gravity, but all the fundamental forces, tearing apart atoms, atomic nuclei, and even the fabric of space-time itself. Current observations favor the simplest model where dark energy behaves like a cosmological constant. Data from the Planck satellite, combined with supernova observations and measurements of the cosmic microwave background and galaxy clustering, indicate that dark energy's equation of state parameter is very close to 1, exactly what would be expected for a true cosmological constant. Massive galaxy surveys are working to map the history of cosmic expansion with unprecedented precision. Projects like the Dark Energy Survey monitor billions of galaxies to trace how the expansion rate has changed over the past several billion years. The Dark Energy Spectroscopic Instrument, DESI, is measuring redshifts for 40 million galaxies to create the most detailed three-dimensional map of cosmic expansion ever attempted. These surveys use multiple complementary techniques to study dark energy. Weak gravitational lensing measures how dark energy affects the growth of cosmic structure. Baryon acoustic oscillations provide a standard ruler for measuring distances at different cosmic epochs. Galaxy clustering patterns reveal how structure formation has been influenced by the competition between gravitational attraction and dark energy's repulsive effect. Some theorists have proposed that dark energy might not exist at all. Modified gravity theories attempt to explain cosmic acceleration by changing Einstein's equations rather than adding new forms of energy. These theories modify how gravity behaves on the largest scales, potentially producing apparent acceleration without requiring exotic energy components with negative pressure. However, modified gravity theories face significant challenges in explaining all the observational evidence. They must simultaneously account for cosmic acceleration, the cosmic microwave background, Big Bang nucleosynthesis, and galaxy formation, a tall order for any alternative to the standard model. The ultimate fate of the universe depends critically on the true nature of dark energy. If dark energy is truly a cosmological constant, then cosmic acceleration will continue forever. The universe will expand exponentially, gradually diluting all matter and energy until space becomes cold and nearly empty. In this scenario, distant galaxies will eventually disappear beyond our observable horizon as space expands faster than light can travel. Our local group of galaxies will become increasingly isolated, forming an island universe surrounded by empty space. Star formation will continue for trillions of years until all the gas is exhausted or dispersed, leaving behind white dwarfs, neutron stars, and black holes as the dominant objects in the cosmos. Even these remnants won't last forever. According to Stephen Hawking's predictions, black holes slowly evaporate through quantum radiation. The largest black holes will take about 10 to 100 years to completely evaporate, leaving behind only elementary particles in an ever-expanding, ever-cooling universe. There's a puzzling aspect to dark energy's current dominance called the cosmic coincidence problem. For most of cosmic history, matter dominated the universe's energy budget. Dark energy only became dominant about 6 billion years ago, roughly when complex life was emerging on Earth. Why do we happen to live at the special time when matter and dark energy densities are comparable? Some models attempt to address this by proposing interactions between dark energy and dark matter. These coupled theories suggest that the two dark components might influence each other's evolution, potentially explaining why their densities became comparable at roughly the same cosmic epoch when observers like us could exist. The fundamental nature of dark energy remains one of cosmology's deepest mysteries. It represents our ignorance about 68% of the universe and potentially points toward new physics beyond our current understanding. Its discovery transformed cosmology from a field focused on gravitational deceleration into one investigating cosmic acceleration and the ultimate fate of all physical reality. The study of dark energy continues to push the boundaries of both observational astronomy and theoretical physics. Future space missions and ground-based surveys will measure its properties with ever greater precision, potentially revealing whether it's truly constant or evolving, whether it interacts with other cosmic components, and what its discovery means for our understanding of space-time and the fundamental laws of nature. Dark energy connects the microscopic scales of quantum physics with the global geometry of space-time, exemplifying how properties of the vacuum can determine the evolution of the entire cosmos. And yet, for all our discoveries about cosmic expansion and dark energy, we still haven't answered the fundamental question that started our journey. What actually caused the Big Bang itself? When we try to trace the history of the universe all the way back to the very beginning, we encounter a mathematical cliff beyond which our understanding simply breaks down. The initial singularity represents the ultimate frontier of human knowledge. If we extrapolate Einstein's equations backward in time, they inevitably lead us to a moment 13.8 billion years ago, when the entire observable universe was compressed to a point of infinite density and infinite temperature. At this mathematical singularity, the known laws of physics simply cease to apply. This isn't just a problem with our current theories, it's a fundamental limitation. At the singularity, space-time itself becomes meaningless. Distance, time, causality, all the concepts we use to understand reality break down completely. It's not that we don't know what happened before the Big Bang, it's that before may not even be a meaningful concept. The heart of the problem lies at what physicists call the Planck scale. At lengths smaller than about 1.6 x 10^33 inches, times shorter than about 5.4 10^44 seconds, and energies greater than about 1.2 Su's 10^19 GeV, quantum effects of gravity become so strong that our current theories can no longer describe what happens. This is the realm where a complete theory of quantum gravity would be necessary. Several approaches attempt to resolve the singularity problem. Loop quantum gravity proposes that space-time itself has a discrete, granular structure at the Planck scale, like pixels on a cosmic computer screen. In this theory, the apparent singularity is replaced by a quantum bounce, where the universe contracts to a minimum size and then rebounds into expansion without ever reaching infinite density. String theory offers a radically different perspective. It suggests that the fundamental constituents of reality are not point particles, but tiny vibrating strings existing in 11 dimensions. In string theory, the singularity problem might be resolved because strings have finite size. They can't be compressed to a true mathematical point. The extra dimensions of space might also provide room for the universe to avoid infinite compression. Some models propose that our Big Bang was actually a big bounce. In these scenarios, our expanding universe emerged from the collapse of a previous universe. Quantum effects prevented complete gravitational collapse, causing space to rebound into a new cycle of expansion. This could potentially extend cosmic history infinitely into the past, with no ultimate beginning at all. Cyclical cosmology takes this idea even further. Models like the ekpyrotic universe suggest that our three-dimensional space is like a membrane, or brain, floating in higher dimensional space. Periodic collisions between brains could create the appearance of big bangs, generating infinite cycles of destruction and renewal without any true beginning or end. Perhaps the most radical proposal is that the universe created itself from nothing. Quantum mechanics allows for the spontaneous creation of particle-antiparticle pairs from empty space. Some theorists suggest that the entire universe could have emerged as a quantum fluctuation from pure nothingness, with the positive energy of matter exactly balanced by the negative energy of gravitational fields. But even if we could understand how the universe began, an even more unsettling possibility emerges. What if our entire observable cosmos is just one tiny region of a vast, perhaps infinite, multiverse? This idea emerges naturally from many models of cosmic inflation. If inflation is eternal, as many theories suggest, then exponential expansion continues forever in some regions while ending in others. This would create an infinite number of bubble universes, each with potentially different physical laws and constants. Our observable universe would be just one bubble in an endless cosmic foam, most of which remains forever beyond our reach. String theory makes this multiverse idea even more concrete. The theory allows for an astronomical number of possible vacuum states, perhaps 10,500 different configurations, each corresponding to a universe with different particles, forces, and physical constants. This string landscape would contain universes with every possible combination of physical laws. This raises profound questions about why our universe has the properties it does. Many of the fundamental constants of nature seem to be precisely tuned to allow the existence of stars, galaxies, and life. If the strong nuclear force were just 5% weaker, no carbon would be produced in stars. If it were 5% stronger, stars would burn out too quickly for life to develop. The anthropic principle offers a controversial explanation for this apparent fine-tuning. Perhaps we observe these specific values not because they were specially chosen, but because only universes with these values can produce observers like ourselves. In a vast multiverse containing all possible combinations of physical constants, we inevitably find ourselves in one of the rare regions where life is possible. Critics argue that anthropic reasoning is unscientific because it makes no testable predictions. It can explain any observation after the fact by claiming that observers could only exist in universes with those properties. This makes some physicists deeply uncomfortable, as it seems to abandon the hope of finding a unique, mathematically elegant theory of everything. The search for extraterrestrial intelligence adds another layer to these questions. Despite decades of searching, we have found no convincing evidence of other technological civilizations in our galaxy. This absence, known as the Fermi paradox, suggests that either life is extraordinarily rare or intelligent species tend to destroy themselves before developing interstellar communication. Various great filters might explain this apparent rarity of life. Perhaps the jump from simple to complex cells is incredibly unlikely. Maybe the evolution of intelligence is a statistical fluke. Or perhaps technological civilizations inevitably discover something: nuclear weapons, artificial intelligence, environmental destruction, that ends their existence before they can spread to the stars. The possibility of alternative biochemistries could dramatically expand the potential for life. While we search for water-based carbon chemistry like our own, life might exist using silicon instead of carbon or exotic solvents instead of water. Such alternative forms of life could thrive in environments we consider utterly hostile, vastly expanding the cosmic habitable zone. Even more fundamental questions arise about consciousness itself. Despite remarkable advances in neuroscience, we still have no idea how subjective experience emerges from objective neural processes. The hard problem of consciousness, explaining why there is something it's like to be aware, remains as mysterious as ever. Some philosophers argue that consciousness might be a fundamental feature of reality. Just as mass and electric charge are basic properties of matter, perhaps consciousness is a basic property that emerges under certain complex arrangements of information processing. If so, the universe might be far more filled with subjective experience than we imagine. Computer simulations raise even more unsettling possibilities. As our computational power grows, we're creating increasingly realistic virtual worlds. Some philosophers seriously ask whether we ourselves might be living in an advanced simulation created by a technologically superior civilization. The implications are staggering. Our entire reality could be nothing more than information processed by some vast computer. These questions push us beyond the boundaries of traditional science into philosophy, theology, and pure speculation. Yet they emerge naturally from our best current understanding of cosmology and physics. The very success of science in explaining cosmic evolution has led us to confront the deepest mysteries of existence itself. What we've discovered about the universe is simultaneously humbling and amazing. Wow. We've learned that the cosmos is far stranger and more wonderful than our ancestors could have imagined, filled with dark matter, dark energy, and processes operating on scales of space and time that dwarf human comprehension. Yet we've also learned that the same physical laws that govern falling apples also govern the birth and death of galaxies. The question of what caused the Big Bang may ultimately be unanswerable. It may require concepts and mathematics that are fundamentally beyond human comprehension, or it may push us into realms where the very notion of causality breaks down. But the search for answers continues to drive us forward, revealing new wonders and mysteries at every step. These frontiers of knowledge illustrate that even with extraordinary scientific progress, the deepest questions about existence, consciousness, and purpose remain open to investigation and speculation. So where does this leave us? We've traveled together through 13.8 billion years of cosmic evolution, from the violent birth of space and time itself to the emergence of galaxies, stars, planets, and ultimately consciousness. We've traced a coherent narrative that stretches from the first fraction of a second after the Big Bang to the formation of the complex structures we observe today. Our current understanding represents one of humanity's greatest intellectual achievements. The lambda CDM model successfully integrates Einstein's general relativity, quantum mechanics, and particle physics into a unified framework that explains an extraordinary range of cosmic phenomena. From the cosmic microwave background radiation to the large-scale distribution of galaxies, from the abundances of light elements to the accelerating expansion of space itself, our model makes precise predictions that match observations with remarkable accuracy. The precision of modern cosmology is truly breathtaking. The Planck satellite has measured fundamental parameters of the universe with uncertainties of less than 1%. We know the universe is 13.98 billion years old, that space is geometrically flat to extraordinary precision, and that the cosmic inventory consists of approximately 5% ordinary matter, 27% dark matter, and 68% dark energy. This represents a triumph of observational astronomy and theoretical physics working in concert. Three independent pillars of evidence: Big Bang nucleosynthesis, the cosmic microwave background, and large-scale structure formation, all converge on the same hot Big Bang model. The agreement between these completely different types of observations provides compelling validation for our understanding of cosmic evolution. Yet, for all our successes, we must remain humble about the limits of our knowledge. The nature of dark matter and dark energy, which together comprise 95% of the universe, remains fundamentally mysterious. We can measure their effects with exquisite precision, but we have no idea what they actually are. This represents one of the most profound gaps in human understanding of the physical world. The detection of gravitational waves by LIGO and Virgo has opened an entirely new window on the universe. These ripples in space-time itself allow us to observe cosmic phenomena in ways that were impossible just a decade ago. Future gravitational wave observatories may even detect the primordial gravitational waves generated during cosmic inflation, providing our first direct glimpse of the universe's earliest moments. Upcoming missions promise to push our observational capabilities even further. The Euclid Space Telescope will map billions of galaxies to trace the evolution of cosmic structure with unprecedented precision. The Roman Space Telescope will conduct deep surveys of the early universe. Extremely large ground-based telescopes with mirrors over 100 feet in diameter will peer deeper into space and time than ever before. But even as our observational power grows, the ultimate question that began our journey remains unanswered. What caused the Big Bang itself? This question pushes us beyond the boundaries of known physics into realms where our current theories break down. The initial singularity represents a fundamental limit to human knowledge, at least with our present understanding. Theoretical speculations abound, but they remain exactly that, speculations. Models of quantum creation from nothing, cyclic universes, the multiverse, and extra-dimensional scenarios offer intriguing possibilities, but none can be definitively tested with current technology. We may be approaching questions that transcend the reach of empirical science, at least for now. The cosmological constant problem illustrates just how deep our ignorance runs. The discrepancy between theoretical predictions and observed values spans 120 orders of magnitude, the largest mismatch in the history of physics. This suggests that our understanding of quantum field theory, general relativity, or both, is profoundly incomplete. The apparent fine-tuning of physical constants for the existence of complexity and life raises profound questions about the nature of reality itself. Whether this reflects genuine design, anthropic selection among multiple universes, or simply the limits of current understanding remains hotly debated. The answers may have implications not just for physics, but for philosophy and our understanding of our place in the cosmos. The quest for a theory of quantum gravity remains one of the central goals of theoretical physics. Such a theory promises to shed light on the nature of singularities, the information paradox of black holes, and perhaps the quantum origin of spacetime itself. String theory, loop quantum gravity, and other approaches continue to make progress, but a complete understanding remains elusive. High-energy particle physics experiments continue to probe the frontiers of the Standard Model. The Large Hadron Collider and future accelerators may reveal dark matter candidates, extra dimensions, or other new physics that could revolutionize our understanding of the cosmos. The connection between the smallest and largest scales of reality continues to yield surprises. The search for extraterrestrial life represents another frontier with profound implications. From microbial life on Mars or the moons of Jupiter to technological civilizations around distant stars, the discovery of life beyond Earth would fundamentally change our perspective on our cosmic significance. The James Webb Space Telescope and other instruments are beginning to analyze the atmospheres of exoplanets, searching for the chemical signatures of life. Advances in artificial intelligence and quantum computing may provide new tools for understanding the universe. These technologies could enable simulations of cosmic evolution with unprecedented detail, help us analyze vast astronomical data sets, and perhaps even tackle theoretical problems that are currently beyond human mathematical capabilities. Yet, even as we push the boundaries of knowledge, we encounter questions that may be fundamentally unanswerable. The nature of consciousness, the reason for existence itself, the meaning of it all, these questions may transcend the scope of empirical investigation. Science is extraordinarily powerful, but it may have inherent limitations when confronting the deepest mysteries of existence. Our 13.8 billion-year cosmic story may represent just the opening chapter of a much longer narrative. Star formation will continue for trillions of years before the universe exhausts its supply of hydrogen. Even after the last stars burn out, exotic processes like proton decay and black hole evaporation will continue for unimaginably long periods. The future evolution of the cosmos may dwarf the history we've traced so far. The cosmic perspective reveals both our physical insignificance and our profound uniqueness. In a universe spanning 60 billion trillion miles and containing hundreds of billions of galaxies, each with hundreds of billions of stars, we are indeed tiny beyond measure. Yet we appear to be the only known observers capable of contemplating these vast scales and understanding our cosmic origins. Modern cosmology exemplifies the deep unity of the natural world. The same quantum mechanics that governs atoms also shape the largest structures in the universe through inflation. The nuclear physics of stellar cores connects directly to the chemical composition of our bodies. The gravitational physics that describes falling objects also governs the expansion of space itself. The observable universe contains roughly 100 billion trillion stars, a number so large it defies human intuition. Yet this staggering complexity emerges naturally from the interplay of simple physical laws operating over cosmic time. The intricate structure we observe today traces back to tiny quantum fluctuations in the first instant after the Big Bang. The cosmic microwave background radiation preserves a direct photograph of the universe when it was only 380,000 years old. This ancient light carries information about physical conditions in the primordial cosmos, allowing us to study processes that occurred when the universe was less than 0.03% of its current age. Cosmic archaeology, through the study of ancient stars and their chemical compositions, allows us to reconstruct the history of element production. We can trace how generations of stars gradually enriched the universe with the carbon, oxygen, and iron that make planets and life possible. The calcium in our bones, the iron in our blood, and the oxygen we breathe were all forged in the nuclear furnaces of stars that died billions of years ago. The possibility of a vast multiverse with different physical laws in different regions suggests that our observable universe may represent just a tiny sample of a much larger and more diverse reality. If so, the physics we observe may be determined more by the requirements for observers to exist than by any fundamental necessity. Future developments in quantum gravity may reveal whether the apparent singularities of general relativity are genuine features of reality or artifacts of our incomplete understanding. The resolution of this question could profoundly change our picture of cosmic origins and the nature of space and time. Observational cosmology continues to accelerate at a breathtaking pace. The next decade promises discoveries about the first galaxies, the nature of dark energy, and possibly even the detection of life beyond Earth. Each new observation has the potential to overturn our understanding or reveal entirely unexpected phenomena. The intellectual journey of modern cosmology, from philosophical speculation to precision science, demonstrates the remarkable power of the scientific method to reveal truths about physical reality. Through careful observation, mathematical analysis, and theoretical reasoning, we've been able to reconstruct the history of everything we observe, from the smallest atoms to the largest galaxy clusters. Yet we remain at the very beginning of our cosmic exploration. Emerging technologies and future theoretical developments promise even deeper insights into the fundamental nature of existence, consciousness, and the universe itself. The questions that seem unanswerable today may yield to the curiosity and ingenuity of future generations. The original question about what caused the Big Bang remains open, but our search for answers has fundamentally transformed our understanding of humanity's place in the cosmic vastness. This quest for fundamental cosmological knowledge continues to represent one of the noblest expressions of human curiosity and our capacity to understand the universe that gave us birth. If you're still awake, it's because the content was really good. So take a moment, leave a like, and subscribe to the channel. It helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.